Alright, let's go. Number 10. The dimensional collapse. In the late 1990s, Jan Ambjörn, Jerzy Jurkiewicz, and Renat Lal were not trying to rewrite cosmology. They were trying to fix a broken calculation. Earlier attempts to build quantum spacetime out of tiny triangular building blocks kept producing garbage, universes that crumpled into a single point, or stretched into a thin, one-dimensional thread. The standard expectation, going back to Stephen Hawking's Euclidean path integral approach, was simple. Sum over every possible geometry a quantum universe could take, average them together, and a smooth, familiar four-dimensional spacetime should fall out naturally, the way random paths average into a straight line. It didn't. Not until the team added one rule: cause has to come before effect. Time can't loop back on itself inside the simplices. The moment they imposed that single causal constraint, something changed that nobody had predicted. In their 2005 paper Spectral Dimension of the Universe, published in Physical Review Letters, Ambjörn, Jurkiewicz, and Lal measured the dimensionality of their simulated spacetime using a diffusion process, literally letting a random walker wander through it and timing how it spread. At large scales, the universe measured almost exactly 4 dimensions, matching ours. At the Planck scale, roughly 10 to the power of negative 35 meters, the dimension dropped to approximately 2. Physicists tried to explain it away. Some proposed it was a numerical artifact of the simplex construction, ruled out when the effect persisted across different lattice resolutions. Others pointed to asymptotic safety, a separate quantum gravity approach developed from Steven Weinberg's 1979 proposal, which independently predicted the same two-dimensional reduction at short distances. The agreement between two unrelated frameworks made the artifact explanation harder to sustain. No one has produced a mechanism explaining why dimensionality would change at all. Whatever you're touching right now, the phone, the desk, your own skin, is built from spacetime that, at its smallest conceivable scale, may not have had the geometry it has now. 4 dimensions might be something the universe grew into. What forced 2 dimensions to become 4, and what decided it should stop there? Every one of these theories agrees on one thing. Something existed before what we call the beginning. Number 9. The string gas. In 1989, Robert Brandenberger at McGill University and Kamran Vafa at Harvard were working through an old, unglamorous problem in string theory: why does the universe have exactly 3 large spatial dimensions, when the mathematics of superstring theory demands 9? String theory's standard picture holds that all 9 spatial dimensions began compactified, rolled up impossibly small, like a drinking straw so tight it looks like a line. Inflation was assumed to have expanded 3 of them by brute cosmic force, leaving the rest curled up for reasons that remained largely unexplained. Brandenberger and Vafa found something stranger. Strings can wind around compact dimensions like rubber bands around a pencil. For those windings to unwind and let a dimension expand, the strings have to intersect and annihilate each other. Run the geometry, and that process only works efficiently in 3 spatial dimensions. Any more, and the winding strings statistically never meet. The mechanism requires no separate inflatant field. 3 large dimensions aren't a cosmic accident smoothed out by inflation, they are the only outcome string topology permits. The theory further predicts specific, testable fingerprints, distinct patterns in the polarization of the cosmic microwave background and in the primordial gravitational wave spectrum, differing from standard inflationary predictions. Objections followed quickly. Critics noted string gas cosmology struggles to naturally produce the nearly scale-invariant density fluctuations inflation explains so cleanly, a persistent weak point defenders have never fully resolved. Others questioned whether the thermal string gas phase is stable long enough to matter. The model survives, unrefuted but unconfirmed, a minority position in a field dominated by inflation. If Brandenberger and Vafa are right, the 3 dimensions you move through every day were selected. Not by chance, not by force, but by the topology of objects too small to ever directly observe. Why 3? And not the 2 that failed, or the 9 that never got the chance to try? Number 8. The bounce that remembers. Abhay Ashtekar and Parampreet Singh at Pennsylvania State University were extending loop quantum gravity, a framework built to quantize spacetime itself, into cosmological models, hoping simply to remove the singularity that general relativity predicts at the universe's origin. General relativity's standard prediction is unambiguous: run the expanding universe backward. And everything converges to a point of infinite density and zero volume. A true singularity, where the equations themselves break down and physics has nothing left to say. Loop quantum cosmology replaced that singularity with something else entirely: a bounce. Space, in this framework, is quantized into discrete units, and there exists a maximum possible density. The universe didn't begin at a point. It contracted from a previous phase, hit that density ceiling, and rebounded into the expansion we're living in now. In 2015, Ashtekar and collaborators demonstrated that certain long wavelength quantum fluctuations can survive the bounce intact, carrying information from the contracting phase into the expanding one. In 2021, a team led by Ivan Agulo at Louisiana State University identified specific non-Gaussian statistical signatures in the cosmic microwave background power spectrum. Patterns loop quantum cosmology predicts, but standard inflation does not. The failures came fast. Some theorists argued the bounce mechanism only works for a narrow, fine-tuned range of initial contracting conditions, undermining its claim to naturalness. Others pointed out the predicted non-Gaussian signal in Planck's satellite data is statistically marginal, present, tentatively, at a significance too weak to call detection. It has not been ruled out. It has not been confirmed either. If this framework is correct, the faint temperature variations in the microwave sky glowing above you right now are not just an echo of our universe's infancy. They may be a partial transcript of a universe that existed, contracted, and died before this one began. Is the signal in the Planck data a message, or noise that happens to look like one? Number 7. The probability problem. In 1983, Stephen Hawking and James Hartle set out to solve one of cosmology's oldest embarrassments. General relativity requires initial conditions, a starting state handed to the universe from outside itself, with no explanation for where that state came from. Their proposed fix, the no-boundary proposal, was elegant. Time, they argued, doesn't extend infinitely backward. It simply ceases to be a meaningful direction near the beginning, the way lines of longitude stop mattering at the South Pole. There is no edge, no boundary, no external condition required. The universe's quantum state is determined entirely by its own geometry. For 35 years, that was treated as effectively settled. Then, in 2018, physicists Job Feldbrugge, Jean-Luc Lenners, and Neil Turok published a paper in Physical Review Letters showing that Hawking and Hartle's original calculation had used an approximation. When the no-boundary amplitude is evaluated properly, using the mathematically rigorous technique called Picard-Lefschetz theory, the result changes completely. The corrected calculation predicts an ensemble of possible universes overwhelmingly dominated by violently curved, rapidly recollapsing geometries. A smooth, flat, slowly inflating universe like ours sits near the bottom of the probability distribution, vanishingly unlikely among the outcomes the no-boundary proposal itself generates. Hawking, before his death in 2018, disputed Feldbrugge, Lenners, and Turok's method directly, arguing their evaluation introduced its own errors. Neither side has conceded. Two groups of respected physicists remain in open disagreement over the correct mathematics behind the theory that was supposed to explain why any universe like ours exists at all. The proposal built to make our existence a mathematical inevitability may, properly calculated, make it one of the least probable outcomes physics allows. If the corrected math is right, why does the least likely universe happen to be the one you're reading this in? Number 6. The infinite approach. In 1970, Soviet physicists Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, now known collectively as BKL, were working through the general relativistic equations describing gravitational collapse, expecting the approach to a singularity to be smooth and orderly, as most solutions to Einstein's equations are. The standard assumption held that as the universe is run backward toward the Big Bang, space contracts uniformly in every direction, converging cleanly on a single point, the textbook singularity. BKL found the opposite. Near the singularity, space doesn't contract evenly. It oscillates, stretching in one direction while squeezing in another, then switching, over and over, faster and faster, in a chaotic sequence with no fixed period. The universe wasn't approaching the Big Bang smoothly, it was thrashing toward it. In 2001, physicists Beverly Berger and Vincent Moncrief numerically confirmed BKL oscillations occur regardless of initial conditions. The chaos is universal, not a special case. Then, in 2003, Thibault Damour at the Institut des Hautes Études Scientifiques and colleagues showed something stranger still. The pattern of these chaotic oscillations maps directly onto the root system of E10, an infinite-dimensional exceptional Lie algebra, one of the most abstract symmetry structures in mathematics. Attempts to dismiss the chaos as a mathematical artifact of general relativity's limits failed once the E10 correspondence held up under scrutiny. No one has explained why a symmetry structure of that specific kind should govern the final chaotic moments before space-time itself stops making sense. Run time backward far enough, and everything you are made of was once caught in an infinite. Accelerating oscillation, organized, structured chaos, governed by a mathematical object with no known physical origin. Was the structure imposed on the chaos, or did the chaos generate the structure? None of that chaos, none of those bounces, explains what triggered the beginning itself. That's where the list gets personal. Number 5. The collision. In the early 2000s, Paul Steinhardt at Princeton and Neil Turok at Cambridge were troubled by a specific weakness in inflationary theory. Inflation explains the universe's flatness and uniformity beautifully, but it requires a special, fine-tuned starting condition to get going in the first place, the very problem it was invented to solve. Standard inflationary cosmology assumes the Big Bang was a singular, one-time event, an explosive beginning to time itself, requiring no prior cause because none could exist before it. Steinhardt and Turok's Ekpyrotic model, drawing on string theory's extra dimensions, proposed something radically different. Our observable universe exists on a three-dimensional brane, floating in a higher dimensional space alongside a second parallel brane. The Big Bang wasn't a beginning. It was a collision. In their 2001 paper published in Physical Review D, Steinhardt and Turok showed that a slow, gentle approach between two branes, followed by collision and rebound, can generate a flat, uniform, slowly expanding universe, reproducing inflation's successes without needing an inflatant field or special initial conditions. The model predicts the process could repeat cyclically, universe after universe, collision after collision. Critics identified a serious mathematical obstacle almost immediately. The transition through the collision itself, the bounce, involves a genuine space-time singularity that the classical equations cannot resolve, no matter how the branes are configured. Whether quantum gravity smooths that singularity over remains unproven. A separate criticism, raised by André Linde among others, argued the model's predicted gravitational wave signature is too weak to ever be distinguished from noise. If the Ekpyrotic model holds, our universe's origin wasn't a singular miracle. It was a collision in a dimension we cannot see, between two objects we will never directly detect that has possibly already happened before. Is the next collision still to come, and would anything survive it to notice? Number 4. The Eternal Return. Roger Penrose at Oxford spent decades studying black hole singularities before turning his attention to a different kind of ending. The far future of an accelerating, ever-expanding universe, trillions of years from now, when every black hole has evaporated and only massless radiation remains. Standard cosmology treats the beginning and the eventual heat death of the universe as opposite unrelated states, one impossibly dense and hot, the other impossibly diffuse and cold, with nothing connecting them. Penrose noticed something the equations didn't forbid. In a universe containing nothing but massless particles, there is no way to define a scale. No clocks, no rulers. because mass is what gives those concepts meaning. A universe of pure radiation at the end of time is, mathematically, indistinguishable in structure from the hot, dense, radiation-filled universe at the beginning. In his 2010 book and subsequent 2018 paper with Vahe Gurzadian, published through the Royal Society, Penrose proposed conformal cyclic cosmology. The featureless remote future of one cosmic aeon transitions directly, through a conformal rescaling, into the Big Bang of the next. He further claimed to identify circular patterns in the cosmic microwave background. Concentric rings he interpreted as signatures of black hole collisions from the previous aeon bleeding through. The claimed circular patterns did not survive scrutiny. A 2013 analysis by Adam Moss, Douglas Scott, and James Zeben, published in the Journal of Cosmology and Astroparticle Physics, reproduced Penrose's statistical method on simulated random data and found the same circular patterns appeared by chance. The underlying conformal mechanism itself remains mathematically unrefuted, but its only proposed observational evidence has been directly contradicted. If Penrose's structure is real, the heat death awaiting this universe in the unimaginably distant future is not an ending at all. It is the next Big Bang, and something of this universe's last light may already be embedded in ours. If the pattern is real, but the evidence was wrong, how would anyone ever know which aeon they're standing in? Number 3. The bubble next door. Andrei Linde, then at the Lebedev Physical Institute in Moscow, was refining inflationary theory in the early 1980s, trying to solve technical problems with how inflation starts and, crucially, how it stops. Standard single-field inflation assumes the process happens once, uniformly, everywhere, and then ends cleanly, handing off to the hot Big Bang phase in one smooth global transition. Linde found that once inflation starts, the quantum fluctuations driving it guarantee it cannot stop everywhere at once. Some regions end inflation and become ordinary universes, like ours. Others keep inflating forever. The result, formalized through the 1980s, is eternal inflation. An unending process constantly butting off separate bubble universes, each potentially with different physical constants, inside a vastly larger inflating spacetime that never ends. If bubble universes exist and occasionally collide, the collision should leave a detectable imprint, a localized disk-shaped anomaly in the cosmic microwave background. In 2011, Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris, using MAP satellite data, published a search for exactly this signature in Physical Review Letters and identified several candidate disks, including one aligned with the previously known cold spot anomaly, though its statistical significance too low to claim discovery. Follow-up analysis using the more sensitive Planck satellite data failed to confirm the candidate collision signatures at the significance required, and the cold spot itself has since been argued by other groups to be explainable through a large foreground supervoid instead. The bubble collision hypothesis has not been falsified. It has simply run out of data capable of testing it further. If eternal inflation is correct, this isn't the only universe forming right now. It's one bubble among an uncountable, ever-growing number, expanding outward from a process that started once and has never stopped. Somewhere beyond the edge of what light will ever reach you is another bubble already touching this one. Number 2. The universe inside a black hole. Nikodem Popovsky, working on extensions of general relativity that incorporate torsion, a property of space-time standard Einstein gravity ignores, was investigating what happens to torsion's effects during gravitational collapse, a fairly technical corner of alternative gravity theory. Standard general relativity predicts that matter falling into a black hole collapses toward a singularity, a point of infinite density, and that whatever happens beyond the event horizon is permanently causally disconnected from the rest of the universe. Popovsky's torsion-modified equations behave differently, instead of collapsing to a singularity. Torsion generates an enormous repulsive force at extremely high densities that halts the collapse and triggers a bounce. Matter falling into a black hole rebounds into a new, rapidly expanding region of spacetime, causally separated from our own. In his 2010 paper published in Physics Letters B, Popovsky showed the torsion-driven bounce could itself function as an inflationary mechanism. naturally producing a flat, homogeneous expanding universe on the other side of the horizon, with no separate inflating field required. Every black hole in this picture is a seed for a new universe. The proposal predicts a specific, testable consequence. A universe born inside a rotating black hole should inherit a preferred axis from the parent hole's spin, potentially detectable as an anisotropy in that universe's cosmic microwave background. Some analyses of Planck data have reported a mild large-scale anisotropy consistent in principle with such an axis, though mainstream cosmologists broadly attribute the same anisotropy to statistical flukes or instrumental systematics, and the connection remains unconfirmed by any independent detection. If Popovsky's mechanism operates in this universe the way it does in his equations, then every black hole currently forming in every galaxy, including ones with mass measured in our own sun, is not destroying matter. It is planting it, somewhere, as the seed of a universe we will never see and that will never see us. Was this universe born the same way, and if so, inside what? That leaves the theorem none of these models can get around. Number 1. The theorem that won't bend. In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin were not trying to prove anything about the Big Bang specifically. Guth, one of the original architects of inflationary theory, was working through a general mathematical question: could inflation, in any of its many possible forms, be extended infinitely into the past, avoiding a beginning altogether? The hope, shared across much of the field, was that eternal inflation might solve the beginning problem entirely, an inflating multiverse with no start, stretching backward in time forever, so that the question what came before would simply have no answer, because there was no before to explain. Borde, Guth, and Vilenkin proved the opposite. Using only the assumption that the universe, on average, has been expanding, a condition satisfied by essentially every viable cosmological model, including eternal inflation, string gas cosmology, and most bounce scenarios, they showed mathematically that such a spacetime cannot be extended infinitely into the past. It must have a genuine beginning. The Borde-Guth-Vilenkin theorem, published in 2003 in Physical Review Letters, applies with almost no exceptions. Vilenkin has stated plainly that the theorem closes the door on any escape from a beginning, for essentially every model cosmologists have seriously proposed, inflationary or otherwise. The only known loopholes require an average expansion rate at or below zero across all past time. Conditions some cyclic and bouncing models attempt to satisfy precisely to slip past the theorem, including several entries on this list. Whether any of them actually succeed remains a live, unresolved dispute, contested paper by paper. Every alternative on this list, the collisions, the bounces, the chaos, the strings, was built, at least in part, to find a crack in this theorem. None has definitively found one. If almost every viable model of the cosmos requires a true beginning, what forces something to start existing where, by every available definition, nothing existed to start it? None of these 10 theories agree with each other. A bounce contradicts a collision. A collision contradicts eternal inflation. Eternal inflation runs straight into a theorem built by one of its own founders, showing it can't be eternal after all. That disagreement isn't a weakness in the search, it's the most honest signal we have that the question is still genuinely open. Every entry on this list sits not at the fringe of physics, but inside its most rigorously tested frameworks, built by physicists trying to close a gap and finding it wouldn't close. The universe was never confused about how it began. We are the ones still doing the math. If you want to see more videos like this, click the video on screen now.